Welcome to the video lecture for the electric drive. We shall see the dynamics of electric drive first. Let us consider a motor. Right, and you know that in motor there is a lock over here, and from here we can take out the shaft, and by using a coupling like this, we can connect to any other load or any other motor, or we can connect this to the rotor of the generator, or we can connect this to the mechanical load like this. So now this end is the motor and this end is the load. So basically we are going through some terminologies. Obviously a motor is having some inertia, and its own inertia, let it be J0, and the load is there, so load is also having some inertia, let us say that is JL, and motor is giving an electromagnetic torque. So this torque, let us say it is trying to rotate in the clockwise direction with a speed of omega m, and the electromagnetic torque is Tm. So Tm direction is the direction of the electromagnetic torque is the same as the direction of the rotation omega m. And there is a straight coupling between the motor and the load, so the load will also rotate in the clockwise direction at the same speed omega L, so omega L and omega M are equal. Now in this combination, and we can have also one more thing here, the load is there, the load torque is obviously opposite to the electromagnetic torque, so load will try to give our torque in the opposite direction, that is TL. So the net torque difference is Tm minus TL is the torque difference, and the speed over here is omega m. Then we can say that power over input power is equal to Tm into omega m is the input power, which is obviously equals to the TL into omega L. Now the problem that arises over here is, the load may be of load required that the value of omega L is equals to 2 pi n by 60, where n is in revolution per minute. Let us say the value of n is, required value of n is 10 rpm. And there is a very heavy load is to be cast, and high torque is required, and the requirement of TL is equals to, let us say, 150 Newton meter. Now I may not have a motor which is sufficient enough, which is having the same rating of like 10 rpm, n value is 10 rpm and the TL value is 150 Newton meter. So, but I have a motor where omega m is equals to 2 pi n by 60. So for the sake of clarity, this is n is the revolution per minute of the motor, and this is revolution per minute of the load. But I have got a motor which speed is n is equals to 1000 rpm. If my motor speed is 1000 rpm, in that case the required value of Tm will only be 0.15 Newton meter rather than 150 Newton meter. Because if I multiply 1000 into 0.15, it will come 150 watt, and here also it will come, just a minute, this side it is coming 100, okay, 1500 watt, and this side I mistaken over here, this should be 1.5 Newton meter will be there. So if I purchase a motor which speed is 1000 rpm and giving a motor torque of 1.5 Newton meter, this is enough to drive a load having 150 Newton meter and the omega value is 10 rpm only. Thing is that the power has to be remain constant. So we need to think about the rating of the motor which is enough to drive this load, and that is possible if I can have a gear arrangement over here, that we can see that our requirement of omega L is 10 rpm, the omega M is 1000 rpm. So why don't we connect a motor in this manner? Same motor we can connect like this. But we will couple it with a gear box. Then this side will be a very big diameter. The diameter of this is bigger one. So here the whatever the radius, these are this, we can see these are the teeth over here. So number of teeth over here will, let us say N1 is the number of teeth, and here the number of teeth is N2. Here we are driving it at a speed of omega M, and here we are getting the out from with the help of a shaft, and here I am driving it. This one is clockwise, so this is clockwise, so this will rotate in clockwise. Obviously this side of the diameter will also, the wheel will also rotate in the anti-clockwise, and this will try to rotate in the anti-clockwise with a speed of omega L. So what is our objective is to make it convenient that omega L is 10 rpm, whereas my omega M is 1000 rpm. We have taken an example only. So the N1 by N2, the teeth should be like this. If omega M is high, N1 is small. So we can have a relation like omega M into N1 is equal to omega L into N2. So from that we can write N1 by N2 is equal to omega L by omega M, which is 10 by 1000, that is 0.01. So if I can have a gear arrangement in this fashion, so we can obviously achieve this value, desired value of the load speed and desired value of the load torque with the help of a motor having rating of 1.5 Newton meter and 1000 rpm. So that's a reason of like using a gearbox over here. So as we are talking about the dynamics of the electric drive, but we are taking some example to make it understand that why and how these terms are used. So let's continue with the dynamics of electric drive. So the total torque is nothing but Tm minus TL, and let us see what are the formulas what we have. The formulas that we have is, we know that the power is equal to T into omega. So if I say electromagnetic torque Tm into omega, so that is a formula of the power. Power is also equals to the rate of change of energy. So if a body is there having an inertia J0, suppose a motor is there. So what we have seen in the previous circuit is there are two motors, one motor and one load. Now these are J0 and JL, and let us find out the equivalent inertia out of it. Let us say the combination of all this is equal to J equivalent, or J equivalent. So let this motor having the inertia is equal to J EQ, that is the total equivalent in load. And this, because of the electromagnetic torque Tm, we are able to drive this load in the clockwise direction. So the energy that is being total energy can be given as half J equivalent omega m square. This total energy can be given as the total torque. So because there is a electromagnetic torque Tm and also there is a torque called TL, load torque, electromagnetic torque is in clockwise, so load torque will be in anti-clockwise. So obviously instead of writing here Tm, I will be writing here Tm minus TL. So we can write the next line, that Tm minus TL is equals to derivative of this term half J equivalent derivative of omega m square 2 omega m d omega m by dt plus half omega m square derivative of J dJ equivalent by dt. Now here we are getting this entire term, and this side is Tm minus TL into omega m. So what we can write here is, let us rewrite this, Tm minus TL whole into omega m, correct? So let us cut this value of omega m from all. Now what we get left out is Tm minus TL is equal to this 2 to cancel out, J equivalent d omega m by dt plus omega m by 2 dJ equivalent by dt. Now here the two terms are there. One term is that when the speed is changing with time. So now this speed omega m which is running, this may change with time or may not. If this is changing, if it is increasing, if omega m is increasing, it is acceleration. If omega m is constant, we can say it is steady state. If omega m is decreasing, it means deceleration. So like that. So if it is a constant, then this term will be 0. For the sake, let us say this is increasing or decreasing. Let us keep it like this. And now another term is here J equivalent. Now this J equivalent is the inertia of the equivalent mass of, like we can say, J0 and JL. J0 is nearly constant, so there is no change, so derivative of this will be 0. If the load inertia is fixed, if the vehicle inertia is fixed, whatever the loaded is fixed, then this term will also be equal to 0. But if the load is changing with time, gradually there is a flow of water. Suppose you're taking a tanker and water is coming out of the tank continuously, so there is a change in the inertia. So like that. So for example, like this load is constant. So if load is constant, this term will be 0. What left out is electromagnetic torque is equal to J equivalent d omega m by dt plus TL. So this will be the dynamic of the electric drives. Yes, there are some terms that can be added if we consider the friction and windage that we will be doing in the later stage. So here what we discussed is that why we need to have a coupling over here, and power is equal to T into omega. Then we try to derive the dynamic equation, that is the electromagnetic torque Tm minus TL is equal to J d omega m by dt. But in case the inertia is not changing, so this term will also be there. So this is one. In the next video we will learn the 4-quadrant operation of the electric drive.